110 case, the 110 case, then we might, sorry, there's not a branch here. If we had got to a case where we didn't find a match, we wouldn't have found something earlier in the tree to be able to look at. So we wouldn't necessarily know where to forward that packet. It's only when there is an action associated earlier in the tree. So that's essentially the fundamentals of the longest prefix matching. But it's not the, this case where we have one prefix per port, it's not really typical in the internet. It's not really how things look. Really, we end up with, we've got, even those 288 ports, even if they connect to different people, there's a kind of inherent hierarchy in the network, in the internet, where some networks have routes to a lot of other networks. So you're very likely to get multiple prefixes, because even if you think about my Google example, maybe I got signed some addresses and I use them all for search. I got assigned some addresses and I use them for YouTube. I might be announcing 2 prefixes. But equally, you might have some overlapping prefixes like our previous example. So we might have several prefixes that are going to route to the same port. So if we draw that out and look at this example, so you can see here they've got 0 wildcard going to port 1, 2 exact matches, 100 going to port 2, 101 going to port 1, and then one wildcard going to port 1. So you can see here that most packets go to port 1, other than if they're an exact match when they go to port 2. So if we draw that out on the prefix tree, we will attach, we'll go and pick the right node in the tree. This is the full tree again. And we'll say, okay, 0 wildcard over here, there's port 1. 101, there's port 1 down here. The third port 1 is over on the 11 wildcard. And then our exact match for 100 is over here in port 2. So that would be the way that we can lay that out. This is the layout that we just talked about. We just now pruned the things that didn't have actions associated with them. So same approach we've been taking. But we can think about that in terms of a more compact representation. If we look here, then most actions, the 0 wildcard here, the 11 wildcard here, and the 101 here, all go to port 1. And it's only this specific case of 100 that goes to port 2. So we don't really need to have this full representation of the tree. We can think about how to make it more compact. And so we can just say, well, if you match anything, then it's port 1. Any option was down port 1. But now compare the bits down the tree. And if you do find a match in the tree, well, that's where port 2 is. So in this case, we've minimized the size of the tree by not having to store all the different actions to it, by exploiting the fact that we could tell something about how those prefixes are assigned and choosing something that minimizes the number of lookups that we need to do. And so every real router has this longest prefix match functionality. It's an extremely core part of the router. We think a lot about how the efficiency of it is, the memory utilization of it is, because we really want to scale. Like I said, there's about 1 million IPv4 prefixes. You can have more internally as you divide out IP prefixes down, IPv6 prefixes too. So we really want this longest prefix match solution. But this case is one optimization. But there's different optimizations and complexity of solutions that you can take. So we then have various heuristics and optimizations that we can make based on seeing what's actually out there. Like as manufacturers look at what the deployments that they see in the network are, or they observe the global network, or as folks like us do, well, we say, well, we don't need to have exact matches here, or we can exploit the fact that some destinations are more popular than others. We can exploit the fact that some ports on the router have more destinations associated with them. We can think about prefix sizes, because not all, we know that the case is very likely that the internet prefixes can't be longer than /24. So we don't necessarily need to worry about more bits. Same for IPv6. It's very unlikely that we have a prefix longer than a /48 that's going on the internet. So those give us ways to be able to say, well, let's design the way that the LPM lookup works in order to see what we fit in with what we actually see. Another kind of key thing to think about is how quick it is to update. With the control plane and with we're running BGP in the internet. We've got a lot of updates happening, and we need to go and update that tree in order to be able to keep it current with what the state of the actual network is. And so it's not just how quickly, we can look up. we also care about how quickly we can update that tree and keep it current with the state of the world. Okay, so we've done some lookups, and we now know what port something should go out of. That's great. That's kind of the core functionality of a router, right? We said at the start that the point of the router is to look up a packet and forward it based on the destination. But that's not all a router does, and these systems are increasingly complex based on the more functionality that you put in them. The kind of basic IP router we just talked about. It has subset of functionality. It will limit the hardware that you need as well as the software complexity. But there's more and more features that are used in routers to be able to implement different things and different business objectives. And so one of those things is queuing. So rather than just saying, okay, well, we'll take this packet and we'll forward it out this port. And if the port is busy, well, that's bad. We'll have to figure out, we'll just put packets onto the link in whatever order. We might want to think about, well, actually this packet is more important than this other packet. So maybe that customer is paying us more money. Maybe that customer is, maybe that traffic is related to voice traffic, which has a latency bound. I've worked on networks where certain packets are keeping broadcast TV online, and they're very delay sensitive, so they need to be got quickly to the destination. And we don't want to lose them because you lose enough of them and people's TV screens go black and they get pretty unhappy. And so the queuing mechanisms in a line card, which are implemented as a kind of output function, give us ways to be able to, knowing something about the IP packet, to be able to figure out how to send that traffic. And so there's kind of 3 stages to that. First is classification. I said there, well, maybe this packet's more important than another packet. Maybe this is a voice packet. Maybe this is a TV packet. Well, those things are classification. They're about how do we tell for a packet what queue, what subset of function of forwarding behavior we should put it into. And we might have different strategies for that. We might say, well, this whole port, if a packet came in on port 1, then it's a really important packet. If it came in port 2, it might be less important. But for other cases, we might want to look and say, well, there's a mix of traffic on this port. Maybe this voice packet is also got some HTTP traffic, some web traffic alongside it. So we might need to look at something that tells us about the packet. And so that might be other fields of the IP header, like the diffserv code point, the DSCP, some fields in the IP header that let us do that marking. We then have some management of the buffers. So we said, well, okay, there's a lot of traffic coming in. Maybe there's 2 10 gigabit ports coming in, and we need to forward them out the same 10 gigabit port. Not too much traffic to send to that link. Now we could just put it into some memory, hold on to those packets, and send them if there is capacity. But we have to figure out how to manage that memory. Maybe we want to say, well, we shouldn't let that memory get completely full, or we should reserve some room in case we need to hold on to an important packet. So we end up with some mechanisms on the output line card, on the output decision, to be able to say, like, how do we really classify? How do we really want to deal with the fact that we've got to deal with this packet? We've got too many packets to send via this link, and not use all the memory in a uniform way. So that buffer management is another thing. And then the third part of queuing is scheduling. So now we've got all these packets in memory. How do we choose what order to send them out? If we had different packets, then we should maybe, like, if we'd had different queues, maybe the voice packets are really important, and we should get to those first. They really are delay sensitive, so we need to get them out onto the wire as quickly as possible. Maybe other packets we don't come to till later on. Maybe they're more delay tolerant. Equally, should we let all the voice traffic go, or should we drop some of that? Should we say there's no capacity for the web traffic? Those different classifications and different scheduling behaviors of how to put the packets on the wire, again, introduce complexity into the router. And you can kind of see here that we talked about, well, look, we don't have very much time to do these very many cycles to do these functions. The more things that we introduce that the router needs to do, likely the fewer packets it can forward. Or the more cycles we'll need, like the less capacity it's going to end up with. We maybe have the same chip, but it can't do as many ports it's got to do because it's doing more operations per packet. So the overall complexity of these systems, especially because they're designed to work in many different deployments, ends up being pretty high. And so some of the advances in the capacity are to do with limiting that functionality. Today, Google doesn't. On the internet, essentially, the question was, I'll just repeat it. It was, who gets to set the DSCP bits? Who gets to say the classification of a packet? Now, on the internet, we essentially just don't trust anybody, right? If you can send me a packet and tell me it's really important, well, it's really important to you, but is it really important to me? Probably not. Or maybe it's not. So what we do is we bleach the packet. Anything that comes in, we rewrite all the bits to 0. We say, sorry, it's just as important as every other packet, no matter what you thought about it. So there's not really any idea of this kind of differentiated services on the internet. Now, I've worked at providers that are selling private networks to people. And so if I have a customer they're running their office network and I'm providing interconnection, then they can pay me and say, well, actually, this voice packet is more important than another. So in those scenarios, that's where you might allow the customer to set the marking, and they would choose, well, this packet's really important to me, but it ends up being part of the service that you sell. So if the service is basic internet connectivity, usually you don't have any ability to do this control. And but in private networks or in more premium products, in the way the industry would have historically looked at them, you get to choose them. Now, a lot of these things are really to deal with not having engineered a solution to work on the internet. So, services like Skype. Well, people said, well, I get actually better voice quality here via Skype than I got from my phone line. So why wouldn't I just use Skype? And Skype was engineered in terms of the codecs it uses, in terms of the encoding it's using in the packet to work well without having this prioritization. Kind of historical phone networks that we're doing weren't engineered that way. And so it's becoming increasingly irrelevant, I would say, to have this kind of prioritization. But it's often used as a way to manage priority between different bits of the business. So when I was at British Telecom, for example, then if you were a commercial customer, a business customer, then you were more important on the core network than you were if it was a home broadband customer. So that kind of business priority is enforced rather than letting the customer sort of differentiate their traffic. So this being said, a long aside to say there are many complexities that come in. That's one of them, kind of mentioned throughout. There's also a few other things that might make this more complex. Especially where we're not just forwarding a packet based on its destination, we're doing more actions. We're maybe having to take headers off the packet because it's got more stacks of headers on it. Other things like that, we might need to do more, but we're just going to assume that the kind of simplest possible picture, which is there is no classification. Every packet is important as every other one. We'll deal with buffer management in the time-honored tradition of if it's full, we'll just drop it. So we call that drop tail dropping. So if it's full, there's no room for us to store this packet, the link's full, so we can't immediately put it onto the packet, well, just throw it on the floor. And then we'll think about a FIFO scheduler. So the first packet that turned up is the first packet that we send. And that just gives us the simplest possible setup to be able to think about forwarding. And as I kind of described through a couple of the answers there, then there's just many complex scenarios here. And they're really used to kind of implement some of these business objectives that we have for the networks that we run that aren't just forward packets as fast as possible. They're forward packets and think about the service a little bit. And that's where queuing comes in. So, to recap, talked about routers. They have different planes. We talked about the 3 different planes. The control plane, that's used for programming the forwarding entries and dealing with exception packets. So that's where we're running our routing protocols. We're telling the forwarding plane, the data plane what to do. We have the management plane, the oft neglected interfacing with the device, telling it what to do, who it is, and hearing from it what's going on in the network for us to be able to know what the network is running like. And then the data plane, which is really the thing that we want from a router, the packet forwarding. The data plane itself leverages those trade-offs in software and hardware. Where we can use hardware we can live with the inflexibility, but we get the speed. Then we use that hardware. We have dedicated forwarding chips that are doing that. But where we need flexibility, we end up with software, but we have to deal with the fact that it's slower. And the main data plane challenge is this speed. we want to scale to those systems that are 230 terabits per second, and next year will be 400 terabits per second, or in a few years will be 400 terabits per second. We want to deal with that, so we need to be really